Hello, everyone. In my talk today, I'm going to speak about the new FSP code, FSP3, and more specifically, I will speak about assessing fold sleep potential in continuously varying stress field, and I will show you the application of this tool in the data array basing. This work was sponsored by Stanford Center for Induced and Trigger Seismicity. I am Noam Dvoy, and the work was carried out with Professor Mark Zobak from Stanford University. Now, knowing the stress orientation and magnitude is very important because it's the basic for assessing the fold sleep potential. And here on the left, you can see the updated map of the stress map of North America that was published by Longsley and Zobak. And the black lines represent the stress orientation. You can see the right map that in some location, the stress orientation changes fast and dramatically. And this is actually what the new code is trying to solve. How we analyze the fold sleep potential in location in where the orientation of SH max changes in really short distance. So the FSP code is developed by Stanford Center for Induced and Trigger Seismicity, and it's freely available through the SCITS website. And you can see here the address of this website. And the code essentially analyzes the geometrical data and the hydrological data, and with the assumption of more Coulomb criteria in order to see if the faults if the faults potentially can slip. The input parameters that we used for that are the fault strike and dip, the well location and the injection rates, the hydraulic parameters, and the mechanical stress parameters. There's two approaches in the code. One is the deterministic, and the other is probabilistic. Let's look at the deterministic approach. And what you can see here is that when you enter the data, you can actually see what is the pool pressure to sleep. And we've got two examples here. That's like a sporadic fault sets. And this is actually from the data basing. And what you can see here below in the code, that what is the potential rise of pool pressure that is needed for each fall to sleep. Here is PSI, and here on the right in MPA. In the probabilistic, we can define uncertainties in both the geomechanical and the geological parts of the model, and the model use Monte Carlo simulation in order to calculate the probabilistic potential to sleep. Here is an example of the results. Here on the left, you can see a map. In this case, there's a pool pressure model with 4 wells, and the color scales show their pressure rise in those wells and in the area. Here you can see a plot that represents the change of pool pressure in each fault, and below is the FSP values. Here is the point to mention that the intent of the software is to quantify the potential for sleep by fluid pressure increase, and not to predict whether that sleep will occur or not. Now, what's so important and why do we need to improve the code? So here on the left, you can see the example of the Delaware Basin. And what you can see here is that the north part of the basin, this SH max orientation is mainly north-south. In the middle, it turns to east-west, and then down in the down or southern part of the basin, it becomes west southeast. And since the previous versions of the code could calculate the potential only for constant stress orientation values, Langsley and Zovak in this work needed to define specific domains in which the orientation of the SH max is more or less similar. And this problem arises in, for example, in areas such as the Grecian fold that is marked here, in which you don't know exactly what is the SH max orientation. And therefore, in this case, they use two kinds of analyses with orientation of 85 degrees and 128 degrees. The new code can also use different or discrete A phi values for each fault, but I will concentrate now on the example of the SH max orientation. So what is new? We can actually insert into the code discrete stress orientation values and discrete A phi parameters. The A phi parameter is actually a relative magnitude between the three principal stresses. And I will show you a workflow how we built a stress orientation map that can be inserted into the code. First, you need very good value of SH max orientations. One reliable source is the Langsley and Zovak 2020. You can go to this paper website and download the SH max orientations. We advise you to use data points that air quality is between A to C, which will give you much more reliable maps for that. The outcome or what you can get from this data set is three values: the X kilometers, Y in kilometers, and the SH max orientations, in which you can build CVS file. The CVS file could be uploaded to the Shine website in order to build the stress grid. We recommend on this interpolation method that is provided in the Shine website, and the methodology of this tool is fully described in these two papers. And this is the website. The results of the analysis is presented here. Here we try to compare here between fine grid and coarse grid. The fine grid is in blue and the coarse grid is in red. And you actually see that in this case, because we had enough direct measurement points, it looks quite similar. So in this case, we use the coarse grid. And the next step is to smooth or take the grid, to apply the smooth grid and grid it. And we do it with ArcGIS, and that's the grayscale map that you can see here. In the next step, we took the full map. In this case, we took the Ennings et al. New full maps of the Delaware Basin. Also, you can download this map from the CSER website. And we split the folds into segments of 1 kilometers and sample the stress orientation maps in the middle of each segment. We use this data and insert it into the FSP code, and this is the result. You can see that folds that are, this is of course normal folding stress state regime in the Dallow basin, and as expected, higher slip potential is found for folds that are parallel to the SH max orientation marked in red. This analysis was done for pressure rise of around 2 MPa, 30 psi. Now let's compare that with the previous work of Langsley and Zobak. This is actually the same map that you saw previously, but here I use the same color scale just to comparison. And in general, it looks, so again, those are the domains. Again, the same color scale for the full slip potential. And generally, you see the same general view, which folds that are parallel to the SH max have higher potential to slip. But when you get into higher resolution, you see that there's some major and important difference. Let's look again at this integration fold and go back to the figures that I showed earlier in this talk. And again, I used the same color scale for composition. And what you can see here, again, the 85 degrees is more likely to slip than the 128. We get some kind of intermediate values in the smoothed map, but you can see that most of the folds is less likely to slip, although there are some segments with higher hazards. What we do see that smaller folds that oblique to the main fold has actually higher potential to slip. Another example is a new map, again by Henning et al. We can compare this map to previous analysis because it's new. Those are folds that actually penetrates, shallow folds that penetrate the Delaware Mountain group. And what you can see again, those folds, many of them are parallel to the SH max orientation, and then therefore they have higher slip potential. So for summary and conclusion, we adapted the FSP accommodate to continue variation in stress orientation and relative magnitude changes in the 3 principal stresses by the AFE parameter. We tested the code with the new folds map in the Delaware Basin and the Central Basin Transform. The new code is an effective tool for assessing fold slip potential and on different scales of varying stress state and stress orientation environments. And we plan to use it in both natural and induced seismicity future studies. Thank you so much and have a great day.